I don't suppose you worked it out in your head. I worked it out beforehand, and it's fairly impressive. The pile of coins on that square of the chessboard would stretch out to the star Alpha Centauri. It would be about 4 light years away. Well, that's exponential growth. Could you bring in the blue whale, please, Bryson? Thank you very much. Well, this wants to be a blue whale when it grows up. And if it succeeded, it would be somewhere out there on the 57th square, because it only takes about 57 cell generations in order to build a blue whale, which is made of about 100,000 trillion cells. Would anybody like to know how many cells they consist of? Right, yes. We've got a computer program which just converts weight into cells by rough calculation. Come along, what's your name?
Sam.
Sam. Now, would you like to stand on the scales, please, Sam? Gosh, those boots are going to weigh quite a lot on their own, aren't they? Right. 53 kilograms. Right, now that is, Sam has approximately 742 trillion, yes, 742 trillion cells, but it would only take about 46 cell generations to make Sam. Thank you very much. Well, let's now try doing that with somebody a bit bigger. Douglas, would you like to come out and have a... Right, let's have a look now.
Yes, quite a bit bigger.
Right. 110 kilograms, how does that look? Right, 154 trillion, only 47 cell generations, though. Thank you very much, Douglas. So only one more cell generation is needed to make Douglas compared with making Sam. And only another 10 cell generations is needed to make a blue whale. Well, 46 or 47 or whatever it is, by the way, a minimum figure. In fact, it would take a bit more than that, because different bits of people are going on dividing for different lengths of time. The liver cells are going on for a bit longer, kidneys a bit shorter, and so on. So it isn't quite as simple as that. But it does suggest to you how the body manages to control the shape that it is. Because all it has to do is to change the number of cell divisions, very, very fine adjustments to the number of cell divisions that different bits of the body undergo in order to change the shape of that bit of body relative to other bits of body. For instance, in human evolution, compared with our ancestor Homo habilis, the modern human chin is a fairly pointed object. Homo habilis has a rather blunt chin. So in evolution of humans, the chin elongated. I'll just show you that. There's my ancestor, Homo habilis, and there's my chin for comparison. So in human evolution, we had an elongation of the chin compared with the rest of the head. We had other changes, but compared to the rest of the head, the chin elongated. Now that would be a very easy trick to do with the local doubling form of growth, because all you do is you slightly change the number of cell generations that went into building the jawbone there, and you have that effect. In a way, the remarkable thing is that cell lineages stop dividing just when they're supposed to, in such a way that all our bits are about the right size relative to our other bits. Of course, in some cases, cell lineages don't stop growing, notoriously, when they should, and when that happens, we call it cancer. Well, building colossal bodies like us, or like horses, colossal by the standard of their DNA, can be called gigatechnology. Gigatechnology means the art of building things that are at least 1 billion times bigger than you are. It's not a thing that human engineers have any experience of. But humans are already talking about the opposite of gigatechnology, which they call nanotechnology. Just as giga means 1 billion, Nano means a billionth. Nanotechnology therefore means engineering things that are a billionth of your own size. Nanotechnology is taken seriously by some serious scientists, not just madmen. And this is what they visualize may happen in the not-too-distant future. These are red blood corpuscles. This is purely imaginary. These are red blood corpuscles. There's a virus. And here's a nanotechnology robot that's been sent in order to skewer that virus. If nanotechnology ever works, then it will have very revolutionary effects upon our lives. Take surgery, for example. Modern surgeons are highly skilled, and they have what we think of as very delicate instruments like these. But listen to Eric Drexler, the American scientist who's the leading apostle of nanotechnology. He says, modern scalpels and sutures are simply too coarse for repairing capillaries, cells and molecules. Consider delicate surgery from a cell's perspective. A huge blade sweeps down, chopping blindly past and through the molecular machinery of a crowd of cells, slaughtering thousands. Now he turns to the suture, the needle, which is used to sew up, a needle and thread which is used to sew up the wound. Later, a great obelisk plunges through the divided crowd, dragging a cable as wide as a freight train. That's American for goods train, there. Behind it, to rope the crowd together again. From a cell's perspective, even the most delicate surgery, performed with exquisite knives and great skill, is still a butcher job. Only the ability of cells to abandon their dead, regroup and multiply makes healing possible. Yet, as many paralyzed accident victims know too well, not all tissues heal. Nanotechnology holds out the prospect of building surgical instruments small enough to be on the same scale as the cells. And these instruments would be far too tiny to be controlled by a human surgeon's fingers. If that's the width of a goods train, then imagine how wide a surgeon's fingers would be on the scale of cells. A robot as small as that, capable of doing that, would be a very wonderful thing to have, but it's only one, and there are millions and millions of, say, red blood corpuscles to repair. It would only work if the nanotechnology machines themselves were cloned up, were reproduced in exactly the same way as the red blood corpuscles are themselves. Like this immunoglobulin molecule, which is what a doctor might inject into you in the thousands to protect you from hepatitis. It only works because it's in your bloodstream in thousands and thousands and thousands of copies. And that's what nanotechnology depends upon. This is not really nanotechnology because it's a biological object, but that's the kind of thing that nanotechnology would look like. Nanotechnology seems to us very strange, scarcely believable. The idea of machines down there at the level of atoms seems a very alien world, more strange than the life that's imagined on other planets by science fiction writers. Nanotechnology seems to us something new, something in the future. But actually, far from nanotechnology being new and alien, it's old. Vastly older than we, whose bodies belong in the world of big things. It's we big things that are new, alien, strange and futuristic. We are products of a flashy new gigatechnology. Fundamentally, life is based in the world of nanotechnology. Now, you remember I said that cells are made of bacteria and we are made of cells ganging up. Well, there are also colonies of individual bodies, social insects, in which the entire colony can be thought of as one big copy-me digression. This is a bivouac of army ants from South America. This is a great sheet of millions of ants. And the next one? Here are just two ants, not army ants, a different species. That one is the sister of that one. They're both members of the same colony. They're both workers. Both are needed by the colony, and so both are there, even though they're such colossally different sizes. And the next one? This is what it's all about. This worker here is feeding a young queen with wings. Those wings are for carrying the DNA of the colony on into the next generation. The entire colony is one machine geared to passing its DNA on into the future.